Good evening, everyone. My name is Danny Silver. I'm the director of the Institute for Data Analytics at Acadia. And joining me, we have Dr. Andy McIntyre. He's a data scientist at the Institute. And the person that helped set this all up, some of you may be in contact with Kalani Tupper is with us. And then we have two teaching assistants as well, Sid Kaja and Neeroj Shrestha, who are both graduate students at Acadia working in the area of machine learning. So thanks for them being here, and thank you all for joining us this evening. So I'm going to switch now so you can see my screen. Normally we would be pointing out where the food and drink is and the washrooms and stuff, but this is we're now in the days of COVID and we're separated, so this is strictly a Zoom type MS Teams session. So one last thing is before at the very end of the session, I just wanted to start the reminders here because we'll do it a couple times. There will be a feedback form for you to fill out, and we'd greatly appreciate if you could send that into us after the session is over. You'll be getting an email from Kalani with that feedback form. So let me switch over to slides here. Just going to share my second screen. Right, you can see things here like this, and I'll go to full screen mode. Okay, so done our introductions. This is our plan for the evening. We're going to first get you started with Colaboratory, the Google Jupyter Notebook type of environment. And after that, we're going to introduce the basics of really regression and backpropagation neural networks to you. And also a quick introduction to Keras and Tensorflow environment for programming in Python. And then we'll get into what the heck deep learning networks are all about. We're going to take a little break, a bit of a stretch, because it's a 3-hour session. And then we will start talking about convolutional neural networks. And finally, recurrent neural networks which deal with learning time series. So that's the plan. So first of all, a bit of a overview, 500-foot level, is that deep learning is really about the ability not only to classify or make predictions of real values from things like images and audio files and things like this, but it's actually the generation of features that allow us to do that and do this. So traditionally, prior to 2010, 2012. Machine learning persons working in that area had to engineer the features. So if you had an image with a character 3 like this in it, then what you would have to do is extract features such as, there's a vertical line at the top, and then there's a vertical line on the side and a horizontal line at the top and one on the bottom for this 3. And you would extract individual features like this that would then be used using a traditional machine learning method like a shallow neural network or decision tree or just a standard logistic regression in an effort to try to identify that as being a 3 versus a 7 or a 5. So a lot of manual work, and for 20, 30 years, people prided themselves in the image processing area of being able to extract meaningful features from images using various functions like Gabor functions and various high pass, low pass filter type of ideas. In the period of starting in the late 90s and through the 2000s, people started to look more deeply at how could we look at the metaphor of how the brain processes data as it comes into our optical cortex, or occipital lobes, it's called, your brain. And what they found was that we had a series of detectors that could initially take the incoming, we'll call them pixels, into our eyes, and then be able to create edge detectors from those. And from those edge detectors, they were then able to create slightly more abstract, but simple concepts, circles and squares and triangles. And from those, create even more abstract visual concepts. And eventually, we could learn to classify fairly complex things in our field of view as being dogs and cats and trucks and cars and things like this. So methods of doing this started to become clearer, as partly because as the computing resources became more powerful over time, we could run experiments that demonstrated that we understood how things functioned. So the big thing here is that now we have the ability to actually create the features or learn the features from the images themselves, rather than having to engineer them and write specific code to do those things. So this is actually an example of how we can take pixels from images of faces, right? Initially just detecting edges of the face and the nose, the eyes, and then from that building things that look like eyes and ears and nose and parts of mouths, and eventually being able to classify this as being a face or a particular face. So that's the big breakthrough, right? These multi-layer networks, these deep networks, start at the lowest layer of being able to construct minor features, and then from those features create more abstract features, all the way up to systems that are able to classify complex objects. And we'll see that once we get into convolutional neural networks, or CNNs, that we even apply more tricks that we found from the optical and auditory cortex of our nervous system to be able to be more efficient and effective in our development of models from a small number of training examples. So deep learning is really interesting from a variety of areas, from neuroscience, from cognitive science, from philosophy, certainly from computer science and mathematics, and even from a physics perspective. There's a lot of the thinking that's gone into how these systems work can be related back to how systems that have energy fall into relaxed states. And at that point, they're able to do predictions of input to output. So there's a long history in neural networks. It goes back actually back to the turn of the last century, quite honestly. But the modern era really started in the 1980 through 86 period, when a group in California published widely the Back-propagation algorithm, which we're going to be going through. And in 1989, Jan LeCun really started working on the genesis of what's now convolutional neural networks. And along with two others, Jeff Hinton, who's at the University of Toronto, and Yoshua Bengio, who's at the University of Montreal, developed deep learning types of solutions. And together, these three gentlemen, by the way, some of you may know, have won the Turing Award in 2019, actually, for their work in this area. So Canada has a real brain trust in this space, and we're very fortunate in that regard, and are able to call upon these people to lead us in many of the new adventures in machine learning. So there's been a lot of successes applying deep learning, particularly to supervised problems, as well as what's known as unsupervised learning problems, where you're just trying to cluster data into the various categories. And by 2014, convolutional neural networks were doing better than humans, and even groups of humans, at classifying images and using large data sets such as ImageNet, which has millions of images and now thousands of categories of objects. We have a wonderful library of things that can be classified. We also have some really interesting recurrent neural networks that can be applied to time series type of data. So where you're trying to predict the stock market, or trying to listen to a song or a voice pattern to either identify that song or to predict what the next word is in the person talking. So really interesting stuff. And this session is meant to just give you a smattering of what this technology is about, and to actually see some code running with modern libraries that make your work a lot shorter if you're programming working in this area. So I'm going to turn things over to Andy McIntyre now, who's going to tell you about the Google Colab environment. All of you would have already gotten set up and moved your files over and everything. If you're having any problems there, this would be the time to post your questions to Neros and Sid, who maybe can help you. But we do need to get moving along quickly with this. So I'm going to turn things over to Andy, who will be talking about notebooks. Okay, Andy, over to you.
notebook, and it's composed of different cells, and cells can be text blocks or they can be code blocks. And the code blocks, in fact, are executable little Python blocks of code. And I guess the main thing to keep in mind for tonight's session is that we'll be doing a bunch of exercises live that will all require that you're able to execute code blocks like this and be able to see results. But in order to do so, you're going to want to make sure that you're looking in the upper right of this this window that tells you that you get this little green check mark that says, okay, you're connected to the back end. So the cloud service is connected, and you have some RAM and some disk space, and you know, there's a computer behind this book. Otherwise, you're going to find that your cells won't run. So there may become times when you need to reset or restart the runtime, and you'll find that feature right under the runtime menu. And another item that we'll want to use for tonight is this change runtime type. Since we'll be using deep learning and there's quite a computational overhead, and you'll want to switch your hardware accelerator to GPU and save that setting. Now, I believe the line numbers are automatic. That was the only other thing that I was going to add there tonight, Danny. But everybody should be probably familiar with this anyway, since it was in the instructions for the workshop. So I'll give it back to you, Danny.
Okay. All right, thank you. Okay, we're going to launch into talking about what the heck neural networks are, and in particular, give you a sense of how the backpropagation algorithm works. Maybe it would be wise for me just to kind of take a little bit of a poll of our audience and just see what their knowledge levels are. How many people have already worked a bit with neural networks and have had some of the theory? I'll just give you a minute, leave your hand up there so I can get a sense of it. So, so Derek, you're there now, is that right?
Yeah, I'm here now.
Hi, Derek. Maybe you could just give us a little overview of what the students at St. FX have covered in terms of neural networks. Has there been something formally already in the class, in the course?
I believe there's only been one lecture so far, so I'm not sure if that's even been done yet. I was just checking today. Sorry, I've been a bit late popping back in here, so.
Okay.
But like I know.
Any other students?
Yeah, there's a bunch of students here that have definitely done it before, and then there's a bunch of students that's going to be totally new this year.
Okay. All right. Okay. Good. Very good. All right. Let's carry on. And I'm going to go into put this down here and full screen mode here. So one of the first things we have to do is get some language about how we're going to consider our input space and our output space, and we're going to think about the inputs to our neural networks as being a vector, like x1 and x2. So just as an example, this is a case of where on the x-axis where we've got age, and on the y-axis or x2 axis we've got height. And this is meant to be two different classes of people who are distinguished based on their height and age. And the red line is a discriminant boundary that separates those two. So this is a classification problem, sometimes called a concept problem, if you like. You know, maybe these are people that like a particular product, the A group versus the B group, if you like. Now, this line we can describe, of course, in the same way that you describe any line mathematically, the old y equals mx plus b. That's essentially what this is, you know, here. It's saying that this line is 0 at the point of where these coefficients, so this would be the input x1, the age, times some coefficient, w1, plus x2, the height, times its coefficient, w2. And then we have an extra coefficient here. This is usually known as the bias. So if you think of a y equals mx plus b, b was the bias. Well, this is the same, playing the same role as the bias. So it's describing a line in space, and the bias is important because it actually helps us, allows us to orient this line anywhere in space. Without the bias, the line would have to go through the origin. And that would be kind of a bit of a constraint. So we want it to be able to rotate it and move it any way we want to. So this allows that to happen. So if we could orient this line using the appropriate W's, then we can clearly make it the separator between these two classes. Our problem is that we don't know what the W's are to make it work for this set of examples. So each of these O's are an example of the people who like our product, let's say, and each of the stars are those people who don't like our product. If we could determine we're on this side of the line, then we could do something like, you know, if this function, right, is greater than 0, then it's of class A, and if it's less than equal to 0, it's class B. Actually, if it's less than 0, if it's equal to 0, it's on the line, and I guess you'd have to say then you're not quite sure, you don't know. So the problem is, how do we figure out the coefficients, W0, W1, and W2? So now nature seems to have found a way to solve this problem, and they do it with the little axon neurons that are in your body. And neurons have some basic components as shown here. So this is a whole collection of neurons. This is just one of them. And the neuron has its main cell body is called the soma, and it's this long, if you like, projectile of send a message carrying cable, if you like, called an axon, that connects to literally tens of thousands of other neurons in your brain. And your brain has about somewhere in the order of 10 to the 14 neurons, and every one of those neurons has an address book of about 10,000 other neurons. Now, those neurons connect to the next neurons by way of these little guys, these little antennas here. They're called dendrites. And at the point, right here, right at this point where the axon from a other neuron upstream connects with this neuron, we have a synaptic junction or a synaptic cleft right there. And this is where learning is thought to take place. This is the place where you as a young child, you're learning to eat, you know, your cereal with your spoon. This is where differences in neurotransmitters and electrochemical characteristics are taking place that allow you to train to be able to get better and better at that activity. And as you practice a sport or practice a card game or just practice mathematics, same thing is thought to be happening. So we're going to end up, instead of using neurotransmitters, we're going to use just a mathematical abstraction of that, weights of connections here. They can be either negative, inhibitory, or they can be positive, right, excitatory. Now, once enough information has come into the neuron, what it does is it discharges and it sends information down to the next collection of neurons. And those neurons, you know, then transmit finally to muscle neurons, which cause you to say something or to draw something or respond in some way. So I'm just going to check the chat here because I see there's several messages. Okay, still problems with the chat, I see. Okay, people are working on that. Let's keep going. And I think I've lost my screen because I did that. Okay, hopefully everybody can see my screen again. Just quickly throw your hands up there if you can see my screen. Yeah, I think we're good.
Looks good.
Thank you. Okay. Okay, good. Okay, so this is our artificial neuron. So it's meant to replace this guy. Here's our artificial neuron. It takes in inputs from other neurons, which are downstream from it. It passes it through connections which have a weight associated with it. What we're going to do is multiply the input times its weight, and then we're going to sum up each of those. Now you might recognize that that's in algebra, matrix algebra is the inner product, right? So that would be the x vector dotted with the w vector would be the summation of each of the products of those, and then we pass them through some type of a transfer function. Actually, this should have been summation function, not transfer. This is the transfer function. And the transfer function can be one of several different things. We're initially going to think about a transfer function that's a really simple step function that's defined by this. So let's look at this problem, first of all. You should recognize this problem as being the logical OR function. This is going to be a really simple one to learn. So we've got x1, x2, and y. And this is our possible combinations of binary values for x1, 0, 0, 0, 1, 1, 0, 1, 1. And for the OR function, Of course, the only time that our output is a 0 is when both inputs are 0. Otherwise, they're 1s. So in that case, then what we have is a neural network that has to receive the x1 and the x2. Each of those have associated weights. And then over here, we have our bias input. We can't forget about that because remember, without that bias, our discriminate boundary would have to pass through the origin. So we have no input for it, so we fix the input to 1. The weight's going to change, but the input is always going to be a value of 1. Now on these guys, of course, they're going to change depending on what the example is that's given to it. Our challenge is, though, is to be able to create, somehow adjust these weights so that the network can produce the appropriate output. So let's just talk about this for a minute. The activation function in this case is fairly straightforward. The summation of W1 times X1 plus W2 times X2 plus W0 times X0 is going to be pushed. We'll call all of that equal to A. And if A is greater than 0, then we're going to output a 1. And if A is less than 0, we're going to output a, just going to draw here for you. All right, so what we're doing here is if it's a step function. So if this is A, which is our summation, like this, and if this is 0, then if A is positive, we're going to output 1. If it's negative, we're going to output a 0. Now we're going to see that we can soften up this function into something that is more smooth flowing like this. It can be a sigmoid. And it will cross here at 0.5. And we'll see that there's real advantage to having something like that over the step function. But the step function is an easy way to begin anyway. Okay, so it turns out that there's a really simple algorithm for doing this that was discovered, early on back in the 60s, 50s and 60s. And it was called the perceptron learning algorithm. And this being the simple perceptron. And the algorithm goes as follows. We do something really crazy. We just set all the weights to random values, small random values, like, negative 0.1 to plus 0.1. And then we present the first pattern to the network. And we push it through the network with the weights as it currently exists. So initially they're just random. It's not going to produce a very good result. We compute the output, and then we change the output according to this little equation. So we take whatever the weights are and we add on a small little change. So what is that change? Well, this guy, Woodrow, two people, Woodrow and Helf, discovered that it's fairly easy to do. All we have to do is take and change it by this amount. So eta is called the learning rate. This fellow right here, it's a value between 0 and 1. D is essentially the difference between what the network is outputting, Y, and what you actually want. We'll call it T, or in this case. So the target value minus what the network's outputting. So that's what this D is. And then we multiply that by that particular input on that connection. So notice that this WI is just for one connection in the network. It's just for one of these connections we're talking about. We have to think about how do we adjust that one connection, and oops, sorry, this is the method. Now we're going to see in a bit why that works. This is the back-propagation algorithm, but it turns out that they figured this out through trial and error, and it works really pretty well. And if you train a neural network based on this, adjusting the weights accordingly, then it actually builds a pretty good model. Now, what are we doing time-wise here? Yeah, I think I'm going to keep on going. So what is an artificial neural network doing? In the, maybe just before I move on here, in the material that was sent to you, you will see that there is a perceptron XLS file, and that actually walks you through. You should see this like this. That will actually walk you through trying this equation. You'll actually see how the weights can be updated appropriately
to actually end up with values of weights that satisfy the or the and function. I think this one is the, you see it's the and function, this one is, but you could change it to the or function if you like and try it. So it's an active Excel spreadsheet, which you can actually walk through to see how those weights can get updated for the simple little problem, and it works really quite well. So what is an artificial neuron doing when it is training like this? Well, it's discovering what these W0, W1, W2s are. It's adjusting the position and the angle of that discriminant boundary. In the case of the OR functioning, it's positioning it so that the 0 class case for Y is separated from all of the ones. So here's our simple little perceptron with one active node and two input nodes. That's our X1 and X2. Here pictorially, graphically, are the instances, the class instances of 0. That's for the first one. So when our inputs are 0 and 0, it's 0. And when our outputs for any one of the other three are applied to the network, what we want it to do is output a 1 instead of a 0. And if we had a discriminant boundary like this separating these two, then clearly these guys on this side would be a 1, and on this side would be a 0. Now, one way of thinking about what's going on here from the network's perspective, so if I go back and draw this again, is maybe I'll go in red, is you can think about this as being like a ski slope, like this, coming out of the board. So this part down here is low at 0, and this piece up here is high at 1. So everything above this 0.5 point, which is right here, is a 1, and everything below it is a 0. So the neural network's actually creating a third dimension, if you like, coming out of the board that says anything up here is a 1, and anything down in here is a 0. And that shape I've drawn is more logistic or sigmoid function. Ours is a straight step function, but they're kind of the same, pretty close to being the same. So if we turn to this little animation, then what we have is we have another problem. In this case, this is one for detecting people's way of typing. If we had an X1 input of typing speed and the person's X2 as their mistakes, then we would train this simple little perceptron to orient its discriminant boundary so it separates things like very nicely. Now the problem is pointed out by a relatively famous AI guy, Marvin Minsky, in 1969, is that these things are only good for separating stuff that is linearly separable, for which we can draw a line and separate things out really nicely. And a problem that doesn't work out so well, a very simple problem for that, is XOR. There's no way that this neuron can possibly solve this problem here of separating these zeros from those ones with a single line. There's no way of orienting that. And so what I'd like you to do is to turn now to the first tutorial, which is the perceptron IPy notebook. So let me just go to the right place here, notebooks, and open Colaboratory. And you should be looking at this. And we're going to expand these sections. So now this is the first notebook you'll be seeing. Every one of the notebooks, if I collapse this, I'm going to be presented to you basically like this. So the beauty of Jupyter notebooks, and again, just by a show of hand, how many people have already worked with Jupyter notebooks in some way or other? Okay. Oh, excellent. So there's quite a few of you. Oh, that's great. Okay, so Jupyter notebooks, as you know, are great for embedding comments and pictures and video and all kinds of things along with code. And it's a great way to annotate what you're doing and share code and ask questions. So we're going to open this wide. If you go to view and expand sections, then you see that the first thing we're going to do in general is set up the learning environment. And all we're doing is importing things. We're going to bring in a library called NumPy, which if you've written Python code, probably already familiar with. And this is a plotting library. So we're going to do some graphics towards the end here. And you can execute each of these components by just clicking on that little button. It just comes back and says the environment's ready. Now, we don't have to read in any data here. We're not going to encumber you with having to deal with all of that. We're just going to set up the data immediately right in the code. And in this case, we're going to be initially looking at the OR function. So this is the target values for the OR function. The input values are being defined right here. So this is our collection of 0001, 1011. And we also have the biased input. So we're also having our bias of input added on here. So if you run this piece, then you'll see that everything is ready to go. So we've got our bias input, our X1 input, and our X2 input, and this is what we're expecting the network to eventually learn for all of those. So this is a case where we're going to be learning everything, all of the examples in the model. So this is the network architecture, the simple network which runs the logic that we saw, the mathematics that we saw in the equations here. So we set our learning rate to 0.1, that was the AIDA value. We're going to set our number of iterations or epochs to 200. So it's going to go through all those 4 examples 200 times. And this just helps us define the size of our network. There's just 1 output and 2 inputs. And we've got our bias, of course. Setting a random seed is important because we're going to generate random weights. And by having a seed value, we can cause the network to generate the same weights every time. So it's just deterministic from that perspective. We can change it as well if we want to, but this initializes our small weights in the network to small random values. And we're also going to set up an error log where we record the error of the network every epoch, because we're expecting that with every epoch and with every change of weight, the error of the network will decrease over time as we go through the. So this is the code that fits, that should be fitting the model to the data, and it just performs the mathematics that you saw in the slides. The predicted output, first of all, is going to be, it's just checking to see if the weights times the input is greater than 0. If it is, then this value receives a 1. That's what this bit of code right here does. I know that there's no if thing kind of in it, but it trust me, it does. This just returns a value of true or false. So if this is true, then printed output gets the value of true. The weighted output, the weight out, the output of the network, is then going to be equal to, and this is the change in the weight. It's the learning rate times its difference, what we wanted at the output for that example, minus what the network's actually producing. We just generated that here, times whatever the input is. Now you have to keep in mind that we are working here with vectors and matrices. So that's the beauty of using NumPy arrays here, is that in Python, is that we're doing all this with vectors all at once. And then we're recording the error, and the error that we're recording is the difference between the desired output and what we're actually outputting, squaring it, and then we multiply by value by 0.5, which you'll see in a bit why we do that. I also have a bit of code which you can experiment with here. That's the sigmoid function. If you replace this bit of code with this bit of code, so comment this out and turn this one on, you'll see how the sigmoid function operates very similar to the step function. So if you run this piece of code, it runs through the iterations, learns it very quickly. The error on the very first one, oh, that's because it's already run once before. I'm going to do a run all on this. There, the initial error is 0.375. And then the last bit of code here just gives us a sense of how well we've done. It dumps out the error log, and it shows us what we expected as our outputs for each of the 4 examples, and it also outputs what the network is actually doing here. Now, this bit of code is outputting false, true, true. Ideally, that should be 0, 1, and 1. We can actually change that up here. I think by just changing this to predicted. Let's call it out equals. I think times 1. I think that will do it. Yeah. So now, what that did was just convert the truth value to an integer, and so now it's predicting something where you can actually see that it does exactly what we want it to do. Okay. So hopefully you've gotten through that as well, and you can play with it on your own a bit more when you have a bit more time. Let's get back to neural networks and talk a bit more about how things become a little more complicated. Okay, so this is now, that seems great, but the problem is that it doesn't do very well. Oh, sorry, yeah, that would be important to show you. Let's go back up to the top here, and what we're going to do, I'm just seeing a number of things happening on the chat. Let's just see if we've got that worked out. Okay, do we have chat on now, guys? Yeah, I can see the chat now. Oh, that's excellent. Okay,
it looks like in order to get that working, Danny, they had to, and correct me if I'm wrong, Neeraj, that you had to send someone, you have to send the attendees a link, and they have to go out of the meeting and come back in again in order to get the chat working. Is that right?
Yeah, that's what happened. Like I sent the link to one of the attendee from Acadia, and now they can see the chat, except like everyone can't, but he can now. So.
Okay, that's interesting. I don't know why that would be. I do know that I ran into a problem a couple of times with Dalhousie, because we both university had licenses for Office 365 and Microsoft Teams, and but since the 2 organizations were all one big happy family, we ran into a problem similar to that. So maybe it's the same with Saint FX. Whereas if they were coming in under a non-Saint FX email address, they wouldn't have that same problem. Okay. Well, apologies that that's not working as smoothly as we would like. Should have tested it out, I guess, more thoroughly. Let me take you back up here to our perceptron code once again. I just want to show you what happens if we try to develop a model. Instead of learning the simple linearly separable OR function, if we try to train the model on the non-linearly separable XOR function. So you can try this as well. Comment out line 7 in step 1 and replace it with line 9. So you're setting your target values now to indicate that you want the outputs for the XOR function. Now, if you come up to run and click run time and click all, and then go down to the bottom here, what you'll see is that the error bounces back and forth and then never gets any better than 0.26. And that's because the model is not capable, it doesn't have the right stuff to be able to create a discriminant boundary to separate these points. This is what you call a non-linearly separable problem. So that was pointed out by Minsky and Papert back in 1969, and really for 15 years, it really slowed down the work in this area. But we did know that if you have more layers, you can build more complex functions. And in particular, we also knew that if you replace that sharp step sub function with a smoother flowing function, that it was possible to do some really interesting things. And it also was very much more similar to what we saw in nature with neurons in our bodies from neuroscience. But again, how were we going to adjust the weights here as well as the weights down here? So these would work together in some way. So synergistically, that they would work to produce outputs, appropriate outputs. So it wasn't until about 1985, 86 that a solution of this became popular. There were solutions to it, but they weren't widely known. They were for specific problems in physics and engineering. But in 1986, the widely known solution became available. And it became known as the multi-layer back-propagation algorithm. And the idea is that essentially that you backward propagate the error through the network, updating the weights in accord with one another, so they end up producing the appropriate outputs at the outer edge of the network. So conceptually, the idea is fairly simple. What we want to do is to adjust the weights such that the error is reduced as those weights are changed. So this takes us into, calculus. So this is saying that the way to change the weight, Wij, so this is a weight between node I and node J in the network, anywhere in the network, is that we want it to change in accord with how the error changes with respect to that weight. And this guy right here, again, is just our learning rate. And the negative is there because we want to actually point ourselves in the right direction. So for those who have, can we remember Newton's method with curves in physics and chemistry, that, trying to find the solutions can be finding the bottom point, where the derivative is at 0, that type of thing. Well, that's a bit of what's going on here, is that in this case, we're using this derivative as a pointer. We'll call it a gradient. It points downhill as to the direction which we should go in order to update the weights effectively. Now, the error is given to us by the same formula that you saw in the equation in the Python code. It's 1/2 times the desired target value minus the actual output of the network. So for each example, we would have a target output and the network would produce something for it. We take the difference between those, we square it because that emphasizes the big errors. And then if we have multiple outputs, as well as if we have multiple examples, we have to sum them all up. Okay, so this really does require a continuous nonlinear activation function like that sigmoid function in order to work. There's quite a bit of mathematics for this, which I'd be happy to share more information on if you like. But suffice it to say that once you go through the mathematics, there's some fairly simple algebra that drops out of it for the algorithm. And that is that at any point in the neural network, the way to change the weights is according to this equation, which we can modify to be this. So it's eta times a difference factor times the input to that neuron. Now that should look familiar because that's what the perceptron algorithm was doing. Remember, it was eta times the difference times the input. But it's an OI here because it's the output from the layer below it that's coming into the layer above. So for output neurons, this fellow right here is equal to this equation, which when you look at it, it's really kind of odd. It's saying that the way to adjust the weight is to consider what it's outputting right now. But of course, it also takes the difference between what it's outputting and what you'd really like to have at that output. By the way, that should be a J, not TK, it should be J. And then for the hidden nodes, it's a little more complicated because if you think about the neural network like this, when we're changing the weights down here, the output from this not only affects, from this hidden node, not only affects this output, it also affects every other output node. So that means we have to consider the summed change effect upon all of those. So that is that's what this piece is about. So again, there's quite a bit of calculus and then algebra that falls out of that to be able to produce these simple equations. But essentially that's the important breakthrough of the backpropagation algorithm, is finding how to do this. And with this bit of mathematics, we can have a layer of a network of any depth at all. It keeps going down and down and still is capable of training the entire network so it works together. The back-propagation algorithm is basically the same as the perceptron algorithm. You initialize the weights through small random values. You present pattern after pattern to the network. You push the inputs through the network. It produces the output ultimately at the top. You then update the weights according to how the error changes as each of the weights change. And that algebra for that is given here for anywhere in the network. You start at the top, you change those weights, and you come down a layer, change those weights, you come down another layer and change those weights, and eventually you've got them all change, and they work together. You do that a little bit for every example, or every collection of examples, over and over and over again, hundreds, maybe thousands of times. This is why it takes a long time to train networks, and why having graphic processing units and things like this is so important. So what's going on within these networks when they're learning? What's this gradient all about? Well, we can kind of visualize things. This is two of the weights in the network, W1 and W2, and we initially set those weights to some value like up here. We can kind of think about what's going on is that the gradient, which is the y-axis here, the error with respect to how these change, points us in a direction downhill. And if we're lucky, it takes us down to this point down here where the error is really low, and therefore it's satisfying all of the examples. Now, this is just two weights in the network, which could have hundreds of weights, but conceptually, the idea is still the same. It works in that way. Now, if you ended up here, you might go in this direction and maybe not land in such a great spot, or maybe it takes you longer to train to get to a good spot. There is no convergence proof for this algorithm. There's nothing to say that you're going to arrive at a point that's going to be a great solution. So oftentimes you have to rerun the algorithm several times before you do get to a sweet spot, a minimum. We talk about local minimum and global minimums in the error surface. But that's what you can think about what's going on in the neural network as it trains. There's many different variants of this algorithm. One of the simpler add-ons is to add a momentum term, which allows you to kind of move more directly down the ski hill, if you like, right to the bottom rather than swishing back and forth on the sides. So it gets you more quickly to the result. And that's done really easy. All you do is add a little bit of what you added last time to the weight. So right, so you make your change, but you add on a little bit of what you added last time. So that's the idea of momentum. So there is a coefficient for that. So now we've got AIDA, the learning rate, and we've got alpha, which is our momentum term, and it goes between 0 and 9 as well. So it turns out that with a slightly more complicated neural network like this one, we can solve the XOR problem. And if you look at what's going on here, is that this network has actually three little perceptrons at work. It has one here, it has one here, and then has one on top of both of those. So this one actually learns to create one discriminant boundary, and this perceptron, if you like, learns to create this discriminant boundary, and then the output from each of these is passed through yet a third neuron, and it generates, I'm not quite sure why it's doing that. It generates the result. Sorry about that. It's really jumping around on here. Yeah, so these three neurons are working together. So again, this comes back to this idea of generating features from the lowest levels of the input, and then using those features higher up in the network to produce the desired response that we want. So with this more complicated type of network, we're able to now build models that can fit data quite accurately. As a matter of fact, our problem becomes that they can fit so accurately that they are overfit to the training data and don't actually generalize very well. So this is a picture of what happens during training of a neural network. Initially, we've got just a linear discriminant function like this, a line, and as the weights start to get larger in magnitude from their small little random values, we start to fit the data points nicely, right? And then we can start to overfit. to the point where now it does well on the training data, but won't in the future do so well on new examples. So one of the keys to solving this problem is that we actually monitor a second set of data we call the validation set or the tuning set. And early on, the tuning set will show us that we underfit. We're not doing very well in terms of error. We need to get our error down here. So this blue line is the training set error. The red line is the validation set error. The validation set drops and drops and finally hits a minimum, and then it starts to come up. And what's going on here is that the model is now starting to fit so perfectly to the training data that it doesn't do well on predicting for other examples in the test set. This is the model. This is the place where you want to stop training so that the weights are not too overly complicated and produce a model that generalizes well to future cases. So with that in mind, we're going to jump to a more complicated version of the perceptron. This is the back-propagation algorithm. And we go back into notebooks. Now have a look at the MLP, back-prop-an model. Bring up this piece of code. Let me just stop here. Just make sure everyone is with us. Oops, that's not good. There we go. Is everyone now able to load up this piece of code, the MLP back-prop-an? Just throw up your hand if you've been able to do that. Good, thank you. So if you expand this now, everything, the steps are the same. Philosophically, they're the same. The code, of course, is a lot more lengthier because it's dealing with two hidden layers, and it is applying that back-propagation algorithm. I'm not going to spend a lot of time on the details in the code. You can go through that a lot more on your own, but let me hit the high points. The first section, as it's saying here, is we set things up exactly the same as the perceptron. We set up the training data in the very same way. But notice that we're going to work immediately on the XOR problem. So this is our nonlinear problem where our outputs are 0, 1, and 0, 1, 1, and 0. Now, this is the configuration of our network. And as you can see, it's a lot more complicated. We're going to train for a longer period of time. We've got our momentum term here. That was the alpha. We're going to leave it at 0 initially. And our learning rate, we're going to set to 0.1. That's typical of the learning rate, or even smaller. Smaller learning rates never really hurt, other than for the fact that it takes longer to train. Now our hidden inputs are 2. We're going to use 2 hidden nodes, and then we've got our output node. This just randomizes the weights, sets them to small values between, in this case, between plus and minus 0.5. And this dumps out what the weights initially look like. So here's my initial set of weights. And you'll see that there's 9 weights in the network. That's because we've got 2 inputs. If you look at one of our hidden nodes, we've got 2 inputs, and we've also got the bias input for that. That's true also for our output node. So total 3 neurons, active neurons, 9 weights, 3 associated with each. Now this fits the model to the data, and it has all that mathematics in it that you saw on the slides. We generate our output first for the hidden layers, and then we take that output as input to the output layer. We then compute essentially the difference through using the derivative, and this is that algebra, first of all, for computing the derivatives. And then we determine how to update the weights in the hidden layer, and then how to update the weights in the output layer. And then we actually do those updates. And the last thing we do is then just compute the error over of the network on all of our training data and retain that error in our log so that we can print it out. We also just dump out a sense of how well we're doing at each iteration. Well, actually, I'm not printing it out every iteration. The little if statement here checks to see if we've gone through it 100 times. And then after 100 times, it prints it out, and then 200, and then 300. So that's what this bit of logic will do. So if you just run this whole body of code by clicking run and all, let's see that it very quickly runs for 20,000 iterations, and it starts up quite high, spends quite a bit of time up there at that height, and then finally finds a part of the ski slope that goes downhill and dives down the hill towards the valley, if you like, discovering that low point in the error surface where it's doing well for all the examples. And pictorially, you actually see that here in this graph. Stays up at these high error values and then eventually drops down to almost no error whatsoever. This was what we desired as the output, and this is what the network is outputting. It's not perfect, it's 0.03, but that's not bad, and 0.96, 0.96. If you let it train longer, you can actually get this closer and closer to 1, and that's easy. You just go back up to the code here and put another 0 on there if you like, and then run it the whole thing again, and it'll run for that much longer. And hopefully at the end of all of that, I guess it's got to train for 200,000 times. So you can even see from this little problem why having a lot of computing power for machine learning is important. So yeah, so now this is what we're getting: 0.007, 0.99, 0.99, and 0.09 training. Okay, so I know that was rapid, not as rapid as I guess we'd like, but pretty much on time given our late start. It's now 7:11. That brings us to the end of kind of the introduction to neural networks and kind of the fundamentals of the back-propagation algorithm. Why don't we just open the floor to see if there's any questions from folks? Take a breather and let Andy get set up for the next section. Perhaps I'll just leave this open for a minute just to see if there is any questions. So
guys, if you have a question,
up.
please speak up. Like the chat is not working right now. We are working on it. If you have a question, please unmute your mic and speak up.
Yeah, by all means, open up your mic and just go ahead and ask the question.
So this is less a question, but more like something I should raise, a bit of a thing to take note of. But some of the results I got on my end weren't quite the same as what you got. And I noticed that when you mentioned there was like the 100 thing that you made a mention of, mine was set at 50. So the code might be a little bit different on my end.
Oh, right. Okay. Yes. All right. I see what you're saying. So that this is the backprop code or the perceptron code you're referring to?
I'm talking about the code we basically just looked at, so not the perceptron.
Okay. So where was the 100 value?
Should be closer to the bottom. Oh, here we are. Step 3, close to the bottom.
Step 3, close to the bottom.
The highlighted line there.
Oh yes, right. Yeah. If you had yours at 50.
Yeah, that's what it was by default. By default, it was at 50.
Yeah. Okay. And it's going to generate the output slightly. So that's every 50 iterations. It's not doing anything different in terms of the calculation of the actual weights and the model. It's just yours is dumping out the output every 50 iterations. Mine was just doing it every 100 iterations. That's all.
Also, the graph looks different too.
Okay. I guess I'm surprised at that, but
I did change. Well, I did change mine to.
Yeah, well, if you change others, so with the default values, I guess you should have been getting something like this. If you changed other values, naturally it will make for different results. But given that you're training for 20,000 iterations, and that's really the important thing. If you're training for 20,000 iterations, you should have seen something like this. Because that other bit of code you just mentioned doesn't have any effect upon the graph. Because the error is actually logged every iteration. So yeah, this only affects the printout here on the message. You are getting good results though, regardless. Is that right? Your model's actually developing a solution.
Okay. All right. This time around, the graph I ran does seem to be more similar now.
Okay. Okay. Good. Anything else from anyone? If anyone not able to run the code or have any really significant problems?
I see two hands up in the attendees list there, Danny. I don't know if those are people who have a question or maybe they just had their hand up and forgot it.
So there's Chao Zhu and Alpha Hossein Mohammed, I think. So I think Chao heard me. Alpha, are you there? And no question? Okay. Don't mean to pick on you guys. Just want to make sure that there was any questions. Does anybody have anything? Again, I realized really quick on a topic that, normally in a classroom, we probably would spend, at least a week to 2 weeks covering all the ins and outs, but it gives you the flavor of things, and you've got some material here that you can examine in greater detail on your own. Okay, I'm going to turn things over to Andy.
I think you're up next again, Danny, with the TensorFlow and Keras.
Oh, okay. So sorry.
And then there's one more little piece there to complete, and then I'm up. You get a break after that.
Okay. All right. Let me get rid of these guys here. And okay, in which case I wasn't on time. I'm over. I'm going to do this one really quick here, guys. Bit of a history lesson here, which I guess is perhaps become increasingly less important. As you notice, there was a lot of code there. You wouldn't have to deal with all that code all the time, particularly for really deep networks with lots of inputs and lots of hidden nodes. So libraries of code were created to actually make this simple. And because a lot of computation is required, the use of graphical processing units and now tensor processing units have become popular. And it would be nice to have libraries that can take advantage of that automatically so that you don't have to code such terrible things. So TensorFlow was created for those two purposes. It provides a great way of describing neural networks, machine learning algorithms, and for executing them really quickly on high performance computing technology. What the heck is a tensor? Well, tensors are really just arrays. So this is a vector, a 1D tensor. This is a basic two-dimensional array. It's also known as a tensor.
Sorry,
and this would be your three-dimensional.
You don't have your screen on.
Yeah.
Oh, so sorry. I exited that for Andy and I forgot to bring it back on. Let's try this again. Right. Anyway, you didn't miss anything until we got to this one. What the heck is a tensor? A tensor is an array, basically. So this is a one-dimensional vector or array, two-dimensional tensor or two-dimensional array, a three-dimensional array, of course. So this can represent, so this would be like if you had your standard set of attributes for predicting disease. So this is the patient's age and blood pressure and temperature and things like this. This would be like an image. Now this can be a video where you've got a series of images one after the other, 3D tensor. And then problems can obviously go up in terms of dimensionality even further on this. And it's nice to be able to work with this generally because it gives you a lot of latitude with problems. What TensorFlow is, it allows you to describe the calculations graphically as a graph. And once you've described it graphically, kind of setting things up then you can just call upon TensorFlow to execute this graph. So what this is showing you is just what we've seen already earlier, is that we've got our X inputs, matrix multiplied by its weights. We add in the bias nodes in this case, and then we pass that through an activation function. In this case, it's a ReLU function, and he's going to tell you a bit more about that. It's like a sigmoid, but it tends to compute a little more quickly. Right now, the TensorFlow programming still looks pretty ugly, although it's a lot of stuff's going on behind in the scenes, and I'm not going to spend too much time on that. What happened was that people said it's got to be easier ways of doing this. There's just so many things we have to set up and configure here. So someone created another library that sits on top of environments such as TensorFlow. There are others too, Theano, PyTorch, and Keras is able then allows a really user-friendly, as it's saying here, a way to create models in a modular fashion so that you can extend them easily, compose and put elements of it together really easily. So you can do things like, for example, take 2 images in or 3 images in and push it through one network to produce a prediction. I'm actually doing something just like that for predicting the weight of grapes from 4 different images in the field. We're trying to predict the yield of the grapefruit. Not grapefruit, the fruit that is grapes, sorry. And yeah, so Keras is it simplifies things even further. Here's a great example. This would be the code in TensorFlow to do a relatively simple calculation. This is the equivalent statement in Keras. It's that easy. There's a lot of assumptions, but smart assumptions made in Keras. You know, clearly you can see here that this is saying that this is a convolutional layer of two dimensions. That there are 32 filters, so 32 individual filters. We're going to find out what those mean. Each filter is a 3x3 in size. It's going to use the ReLU activation function, and it's telling you the shape of the input, in this case images, coming into this part of the network. You'd have to do this in TensorFlow as the equivalent. And trust me that this is even easier than the code you were looking at with the back-propagation algorithm. So it really does simplify things a lot. So if we now turn back to the code against Colab, we're going to execute this piece of code, TF Keras MNIS sigmoid validation. And we're going to see that this is much easier to work with. All the code. So this is the TF Keras MNIS. Oh, sorry, I got the wrong one. TF Keras sigmoid. So you should have Keras MNIS sigmoid val. Big long name. I'm sorry, but in this particular case, we're going to be using the MNIS data set. Now, the MNIS data set is just a collection of handwritten digits, 0 through 9. And the objective, of course, is to be able to classify each of those digits. There's a lot of them, and that's provided in this library. And one of the other nice things about TensorFlow and Keras is that it comes loaded with a whole bunch of example data for you to be able to begin to learn with and trial. And that's true of the MNIS data set as well. So the code is structured as we've done before. The first part loads in, imports all the libraries and things that we need. That's always all basically the same. Tells us the environment is ready and even what version of Keras that we're using. We then set up our learning parameters. Now, given that we have a lot of data here, in fact, we've got about 60,000 examples of zeros, ones, twos, threes, and fours. 60,000, so that would be 6,000 examples of each of the 10 different digits. There are 10 different classes, one for each of the categories that we want to output. Initially, we're just going to train for 3 epochs, believe it or not. That's all that's going to be needed here. This loads in the MNIST data set. That's all we need. The reason it's so simple is because the MNIST data set is part of the environment we're working in here. There's others as well, but MNIST is one of them. And this really, really simple call not only loads the data in where the program can access it, but it further carves it up into a training set and a test set. Now, when we're doing learning, it's important not just to know how well it does on the data we're training on. We want to know how well it's going to do on future data. So that's why we've carved things up into the training set and the test set. X is our inputs, and Y is our target values. This is just indicating whether it's a 0 or 1 or 2 or 3, etc. And then the X test and the XY are its counterparts. Now, the other thing we're doing is we're also creating a tuning set that we can monitor from the data. So our original data has 6,000 in it. Our tuning set is going to have 10,000. Our training set is going to have, I think, 50,000, and then our our test set is going to have the other 10,000. That's weird. That adds up 7,000. What am I doing wrong here? So 50 to, oh, I see. I think that, right, I've cut down the training set a little bit just so it doesn't take so long. That's what's going on here. So right down here, it tells us the truth. Oh no, we have 50,000 in the training set, 10,000 in the tuning set, and 10,000 in the test set. So I guess it was right up here. So that's how we've carved up the data. Now we configure a network. This is all it's to it. With Keras, that's all you have to do. That's configuring a network that has an input layer, one hidden layer, and one output layer. Our hidden layer has a sigmoid activation function, that smooth flowing S function. Our output network has something a little different. It's called the softmax function. It allows us to have 10 outputs, and it's going to try turn one of those outputs maximally and all the others down lower, so that we can know which one it thinks is the output class. So we've got 10 outputs, and we're going to assume the one on the left most is the 0, and then followed by 1, and 2, 3, or 4, or 5. And whichever one of those is most on, that's how we're going to identify which class the network thinks it is. And then we, given that we've defined our network here, so this is setting up that graph of the computation. This does the compile. This is an important step because this is where it's either compiling it for the CPU or alternatively for a GPU or even a tensor processing units. And this does the fit. So once it's compiled, it then says, okay, take the training data, both the input examples and the target values, use the batch size, which says how many examples I'm going to look at once before I update my weights. And for the number of epochs, which is only 3, we train, and this says verbosity. It's just saying how much junk do you want me to print out every iteration that I go through things here. And this is also indicating that I'm going to use a validation set just to kind of monitor and check. So once we've built the model, the only thing left to do is to see how well we've actually performed. And it passes all 10,000 of the test set through the model, which it has not seen, and ends up getting an accuracy of 0.94 just for those 3 iterations. Now, you may wonder, how's it doing that in 3 iterations? Well, that's because there's 50,000 training examples in every iteration. That's a lot of stuff. And within every one of those 50,000, it's actually updating the weights every, what was it, 128 or something like that. So if you run this whole thing, come up here and click Run All, then you should, at this point, actually see, it kicks in here just a second. See it run through the 3 iterations. Takes a little bit. Remember, all this is executing out on some Google Cloud server. And then produces the output. And what we've done in this little bit of code here is actually showing you some of the digits in the test set. It's actually the first 10 values, and it shows you what the predictions were by the neural network. So it's getting them all right except for this one. So there's a couple here, like this one, and maybe this one, which may be a little tricky even for a human to know if it's exactly what you think it is. So this one thinks it's a 6 for some reason. Okay, did everyone kind of get through that all right? And were they able to run that piece of code? Can you give me some high fives? Were you able to get through that? Try it out. Okay, wonderful. Well, congratulations. If you don't have children yet, you just built your first neural networks, just trained your first neural networks, little neural networks. Okay, Andy, over to you.
Okay, thanks, Andy. Let's see how I can, I guess I share my whole desktop here. Okay, folks, just bear with me for a second. All right, so this is kind of all the things that we've heard Danny talking about to this point has sort of led us up to the idea of, building very powerful networks and very powerful models, what we call deep neural networks. Can we see my screen there, Danny? Okay.
Yep, I can see your screen.
Okay, looks good. So if we can get through this section, I think we have a break scheduled right after this. And at that point, maybe we can collect some questions and just check in on how everyone's doing. So bear with me, and we'll get through this in a bit of sample code, and you'll see how it all kind of comes together. I think this is the first step where you start building some really powerful stuff. All right, so what I'm going to do really briefly here is give a little bit of background about why we're building deep neural nets, like what kinds of applications are happening kind of out there. You're reading about them and seeing them on TV every day. We'll talk about the problems with developing deep networks, particularly the problem of vanishing gradient. So these problems that sort of creep in with unstable gradients when you start using more than one or two hidden layers. We'll talk then about the methods that have been discovered for overcoming the problem of vanishing and exploding gradient or unstable gradient, but mainly for vanishing gradient. We'll see that that's a bigger problem. And then we'll do a little demo using many layers on the MNIST data set that you just were playing with a moment ago. So we'll do a little bit more and go a little bit deeper. So in a word, we use deep neural networks because they're incredibly accurate. You can build models that have prediction accuracies that, are well outside of what traditional machine learning algorithms were capable of. And I mean, a lot of these ideas are coming about today and in the past few, say, 8 years, but they're quite old ideas, as Danny touched on in the earlier slides there. The 40s and 50s were when really people were thinking about these kinds of networks and kinds of math that is being carried out within these models. And it wasn't until the 60s, and Danny mentioned Minsky's book on perceptrons, that sort of set everything back for about 15 years. Then, Jeff Hinton comes around and, he completes his thesis on multi-layer networks, and this multi-layer perceptron theory comes about, backprop comes about, this theory of universal function approximation comes about. And then we start seeing in the early 2000s the word deep being applied to artificial neural networks. So it was appearing in the literature around 2006. And then in 2012, the big breakthrough there was in image classification. The ImageNet set, in fact, a network called AlexNet, which is a convolutional neural net, which we'll be talking about in the next deck, ended up really having the ImageNet error rate, which had stood for years, down to around 15%, so an amazing result around 2012 neural nets. We also began seeing in recent years things in our homes and on our watch and our phones, etc. All these things can interpret voice, can interpret, cursive handwriting, can predict what you want to put in your text next, and so on. Even more recently, well, very impressively, I think, in 2016, human competitive results started happening in the games of chess and Go, and later in the game of StarCraft, which you may have played or may not have, but a lot of these were very important deep network milestones and results. So yeah, I mentioned a few there, but I mean, you can Google any of this stuff, and it's very interesting how deep nets have come about. And we didn't get there for free. Obviously, part of what needed to happen in the 2000s in order to start building these many layer networks is that we needed to be able to stabilize the training process, essentially. So previous to some of this work, people were sort of grappling with the idea of exploding and vanishing gradients. So they called them unstable gradients. And the idea is that if the weights get big, then gradients grow exponentially. And I mean by exponentially as a power of the depth of the network. And when I mention depth, I'm talking about how many layers we have beyond the input layer. So in this example, you have this this lower level as the input layer. This would be the first hidden layer, so that's a network of depth 1. This would be the second layer to that network, so now it's a depth 2, and so on and so on. And in practice, these are growing now out to be in the hundreds. Many very typical networks are 150 layers, so you can imagine that when we're talking about small weights or big weights, and these being multiplicative terms over the depth, these basically activations are going to be getting extremely large, and this problem called exploding gradient, or very small, which is known as shrinking or vanishing gradients. So of course the typical feed-forward nets, like we've been looking at in the previous slides, are only a couple levels deep, and so it really doesn't bother them, right, to have some bigger weights, but consider activations in a forward propagation of a signal through a relatively deep network. Let's say there's 150 odd layers. You can talk about this as gradients or activations. So we'll talk about it as activations to sort of keep it simple. Imagine that the weights in this network are all slightly larger than 1. Okay, so as we're activating, we have this multiplicative effect going through hundreds of layers, and values that are slightly larger than 1 multiplied by values slightly larger than 1, so on, are eventually going to add up to extremely large numbers. And what's the result of that? I mean, you say, okay, we have exploding activations. Is that a bad thing? Well, yes, because this causes instability in the back propagation. And what you'll find is the training algorithm may take very large steps. And one possibility is that it just skips over the local or global optima, and we never manage to converge at an optimum. So that's obviously a huge problem when you're trying to train one of these networks. So similarly, consider a network where all the weights are slightly now this multiplicative effect is causing the activations to become smaller and smaller as signals propagate up through the network. So as we're getting into the 150th layer, these activations are, oops, I'm getting a little note here that my network connection might be bad, but we'll keep going, and you can let me know, Danny, if I start to break up.
You're nice and clear here, Andy.
Okay.
Yeah.
We'll keep trucking here. So with vanishing activations, you result in vanishing backpropagation and vanishing gradients when you're coming back through to update the weights. Why is this a problem? Because there's very small values to be backpropped, and essentially what happens is none of the updates happen in the earlier layers of the network. So essentially you have a frozen piece of your deep network that isn't really learning anything, and perhaps you're able to learn enough in the later layers of the network that you still do something about right, and maybe that's okay, but keep in mind it's really stealing resources and it's stealing performance away from your network. So that's a bit about how vanishing and exploding gradients are a problem, and we're looking to correct this instability. That's part of the research that's happened in the last 10 years. And another thing to keep in mind here is that the inputs are not not completely immune to their magnitudes, right? So if you're putting very small or very large values into this network, just be aware that it is going to be sensitive to something like that. So appropriate scaling is something we have to keep in mind, and we'll look at that in our example that's coming up at the end of this deck. Okay, so very quickly, again, vanishing gradient's the bigger problem of the two because training slows to a standstill, and you get all these nodes down in the earlier layers of your network that just essentially die out and are not learning anything at all. You're essentially getting a random activation map, and that's no good for learning. Like, sometimes this works okay, but again, it's a theft of your resources and performance ultimately. So what we need, is a way to ensure that the earlier layers are able to train, right? And they are able to continue updating those weights, and you're able to do effective work. So a few ideas on overcoming vanishing gradient, and these have sort of been put to the test over the years, and we'll look at a couple of the sort of finer points here before we get into our example. As Danny mentioned earlier on, it's always okay to perform longer, very patient training runs. So that just says, imagine we just set a very small learning rate and we very carefully tiptoe through the network and very slowly change the weights. Well, the upside is that you'll probably find some local minima, but this is going to take a long time. Lower learning rate kind of implies that. One idea is that's really kind of come to fruition here in the last 15, 20 years is, I can barely hear someone maybe, but maybe I was echoing here. One of the ideas is—
You're okay, Andy. I can still hear you, Andy. No problems. There was a little echo, but yeah. Okay.
One of the ideas here is you can use what we were talking about when we introduced the Colab environment. You can turn on GPU acceleration, and so through hardware acceleration you're able to kind of get through longer training sessions, and it's not unusual these days for a good sized neural net to train for a couple days. And if you're using images or videos, you may be sitting and training for a couple weeks. But in the past, without this specialized hardware and this highly parallel graphics processing devices, you'd be looking at just a problem that would be impossible. It wouldn't finish in years. So that's really come a long way in helping with some of these issues that have been in the past difficult to overcome when we were looking at deep nets. So that's come along right alongside really with a lot of the theory. One of the other ones that's come out to be maybe not so obvious is to have better weight initialization. We talked about exploding and vanishing gradient. Well, obviously, if you just start out with random valued weights, and some of them are really big or some of them are small, then you can grind to a halt really quickly, or you can just start skipping erratically all over the search space. and that's not what you want either. So there are better weight initialization algorithms. Thankfully, Keras and TensorFlow and many learning libraries now take care of all these little details. But obviously, we need to be aware of what's going on and what controls and parameters we can manipulate when things are going wrong. So we'll talk about better activation functions and regularizers in the next section. Here, by the way, when I'm saying things are going wrong, I'm meaning that they fail to converge, or maybe it's overlearning and memorizing, or maybe it's just having unstable behavior. So when you see things like that happening, then think about these things like activation and regularization, and we'll talk about them a little bit in this next couple slides. So again, a lot of this stuff is taken care of for you by the Keras package and by TensorFlow and by other packages. Like most libraries now have a whole series of activation functions. So they're not just step functions, they're not just sigmoid activation functions or tanh. Those were the kind of popular ones before. What became really popular in the deep learning era was the rectified linear unit. Some people just call it ReLU or ReLU. So it can make a lot of difference when you're training a network what activation function you're choosing. And it might not be the first parameter that I'd pick on for optimization, but just you keep in mind that ReLU, which is shown here in blue right alongside this green soft plus function, is the one that you should be trying most of the time. Just practically speaking, try it first. So green here, that's the soft plus activation function. That's sort of what ReLU is derived from. So for regular ReLU, it's a rectifier to the left of the origin. So down in this region, it just zeroes everything out. And then everything to the right, it's just set to the same value as its input. So value of 1 produces a 1 and 2 produces a 2. So that's sort of an unexplained, maybe sort of unintuitive part of this rectified linear unit function, is that at 0, you sort of don't have a derivative there per se, but in practice what happens is you just choose one at random, a 0 or a 1, and that works fine empirically, though it's theoretically a bit bothersome. Another way to frame this, and sometimes people, after trying the ReLU activation function, they'll try this one in the middle, which is called the leaky ReLU. And what that does is just allows networks to continue to optimize their behavior, even when you're in the region that would have been saturated out in the standard ReLU function. This just gives a little bit of training gradient down below the origin. So there's some parameters that you can pick for this, and we'll see how that sort of works in the exercise. So the other problem with deep learning that we touched on is overfitting. And in fact, overfitting is a problem that just occurs in machine learning, but this is a sort of a big one and a fairly famous one in deep learning, because the networks are so incredibly powerful that they have the ability and they have capacity to learn all the various intricacies of the data set, essentially come up with a memorized version of your training set. And you look, well, this is great, it's doing perfectly in training, but obviously training is not what we're interested in at all. We need to show it as never seen, the test set or validation sets, and then it needs to be able to perform well in that setting. And that's obviously what we call generalization. So one way around overfitting is to simply gather more data. And that's everybody's favorite thing probably, and you think of immediately, but keep in mind it's really expensive. So to mitigate, there's a few other strategies to control how weights are updated. So these control how the training algorithm proceeds. And the idea of regularization is that you're reducing this generalization error without reducing the training error. This is often referred to as model simplification and really amounts to penalizing model complexity. So for example, here we're talking about normalization, weight decay, momentum. Danny has mentioned many of these are featured in Keras, but we'll also see the dropout layer. This is an important one that appears in lots of networks, and something you can think about when you're not getting the right kind of generalization, or you're not getting generalization, it's overfitting. Think about a dropout layer. And the idea of a dropout layer is that unlike a standard net with, say, many deep layers like this, the dropout layer basically creates a bit mask in front of each of the nodes and randomly turns on or off using a hyperparameter probability of dropout, and essentially takes those nodes completely out of the matrix. So they no longer receive connections from the previous layer, and they no longer produce activations for the ensuing layer. And what you get from this sort of unintuitive process is sort of what's known as an ensemble learning style of scenario. So on each epoch, you're treating different layers independently and telling them to drop out at random some number of nodes. And what you're creating is the necessity for it to learning using different sets of nodes and connections. So it's also simplifying the network at the same time, because now you have fewer connections, fewer nodes, and in general, these simplified networks and reduced complexity tend to result in better generalization. So that's just one sort of example that we'll be looking at in our little piece of code that we're going to show here in a moment. So another way of kind of getting around the whole problem of unstable gradients and headaches about training and so forth, long training times and all the things that we would just encounter in the real world is this is becoming really popular now. It's the idea of using pre-trained models, and sort of Hinton and Bengio are coming up with some of this stuff 10, 15 years ago now, but this idea of use of autoencoders to capture just basic features of images and feature maps in a huge training set that might cost way too much for you or I to run on our machines or on our servers. You can then download those models just as sets of weights that have the ability to extract the kind of features that you want in any sort of image classification task, like MNIST or for driving a car or recognizing a face. They're very good. They come pre-trained out of the box, and what you can do is actually just train them a little bit more if you have specialized, like if you have certain plants that you're trying to identify the type of stems, or you're trying to identify a crop versus a weed. These pre-trained models are really gaining momentum. So we'll discuss some other architectures that have come about in the last few years, but let's leave it at the pre-trained models and just say that they're out there, and be aware that a lot of the really powerful work that you're reading about now are using those as a basis, and then training and tuning those pre-trained models to be able to to drive that car a little bit more safely down the back streets, or to be able to pick out certain features in someone's face, etc. So to demonstrate this stuff, we're going to ask that you open this TF Keras MNIST deep. So I think you're just looking for this deep piece, and I'll try to show you as I open it on my machine. If you're using the GitHub link, then it's this one, I guess, right in the middle. So you can pop it open on this. One thing I noticed, Danny, was that it was hard to read some of the text on the screen. So you might want to just pop that up a couple notches when you're going through your notebooks.
Okay.
Okay.
Will do.
Normally what I do is clear the outputs before I start, just in case I've left anything in from the last session. But again, this is going to follow the same 4 steps that we've been doing in the previous tutorials. And this is going to look pretty much the same from the beginning here, because really nothing's changed. You're loading the Keras dataset MNIST, the layers package, which you're going to be doing basically from now on when you're using Keras to create a deep network. Each layer in that network obviously is going to come from this library, and there's all kinds of flavors of networks and different types of layers. It's meant to be modular like that, so you can mix and match layers to a certain degree. These other imports are the same, so I'll run this run anyway. And you got to wait for it to connect sometimes. I notice it doesn't automatically initialize, but this just gives us a good sign that things are looking good. We're going to do the same thing here. I don't know why I had that in there to test if math is still working. And this is going to set up the same training and testing and tuning partitions. So importantly in this notebook, we're going to be using the tuning partition for early stopping as a way to inform an early stopping procedure. So performance on tuning is the early stop criteria, and we'll see how that works in a minute. We'll set up the partitions. It's going to download all those training examples and then split into train, test, and tune. So same way as we saw in the previous example, nothing new is really going on until here. And again, we're going to be creating a sequential model using Keras, and that just means that each layer is processed before the next layer is processed. So you're packing them one on top of another. You can just think of stacking layers together. So the first layer that we add in our network is going to have 512 units. It's going to be a dense layer, so it means it's fully connected. And it says the input shape is 784. That's how many pixels are in each of the MNIST images. And here's one of those dropout layers that I was mentioning previously that's for regularization. So it's able to help us overcome the overlearning problem. It's intended to be able to penalize complexity. And we're using a parameter in here, the dropout rate, I think is the name of the parameter, 0.2. So you'll notice if you do just click over the any given function name, you get these handy tooltips. And this does tell us that the rate is a value between 0 and 1. That's just the probability of losing any given node in that layer. So that would apply to this dense layer. Next thing we're going to do is add another dense layer after the dropout, and it's going to be the same as the input. It's going to use an L2 regularizer, and this is just another penalty term that goes on complexity, and again, it's meant to ensure better generalization. And we apply another dropout layer on top of that. So these are kind of arbitrarily, not arbitrarily, because we know something about how this set ought to work and how we want these models to perform. So another dropout layer of 0.2, you can tinker with these parameters you like. Another one, another dense activation with the softmax output. And lastly, the softmax is going to tell us which class, so which value it's seeing in the image. So 0 to 9, it's going to plot a summary of the network and compile it. So this is the look at the network. It tells us layer types, output shapes, number of trainable parameters. You basically just want to see that it's producing something that makes somewhat sense and that you're not seeing a bunch of errors come up. And the next thing to do is train the model. Now, this is going to work a little bit differently because we are going to use an early stopping criteria here. And the idea with early stopping is that after each training epoch, the model is allowed to look at the validation set or the tuning set and make a set of predictions on it. And what we want to see happening is that validation accuracy is constantly coming down, because that tells us that it's probably generalizing better and better. And the minute that we start to see it come back up, that should be an indication that maybe we've gone too far and maybe we're getting overtraining or overfitting. So we want to stop the model from training after we see a minimal point or like a knee in the, I don't know what you would call it, a valley, or like just a lower optimal in the validation accuracy. And one thing you're going to need to do if you want this to work correctly, I noticed that it throws a warning that you need to call this ACCU. Accuracy, val accuracy rather than val ac. I think that might have just changed here recently. So once you've compiled it, you're going to start the training process. One thing you're going to also want to keep in mind is this patience value is set to 3. So what that says is that you can see the validation accuracy go up as many as 3 epochs in a row without causing an early stop. But as long as it keeps going down, then the training will proceed. And so it's allowed to, the validation accuracy, if you can see it here, of course I've made my thing too large, here we go. So the validation accuracy is being reported here on the right. And you're wanting to see it continually go, I guess, up. Yeah, I'm thinking of the other way around. But up, obviously, since 1 would be perfect. And at epoch number 8, we've already hit the early stopping. And if you're doing this along with me, you'll probably notice that yours didn't stop at 8. It might have gone on to 10 or 15 or something like that. The other thing you want to make sure is that you've got enough training epochs in here. Where was that? I also found that you might want to turn this up to like 30. Since you have early stopping, you don't have to worry. It will hit the brakes when it needs to. So in order to make this go quickly, I'm going to change my runtime type to GPU, since we have acceleratable stuff in our libraries here with this deep network. And we're going to rerun all this stuff. And you're going to see how much more quickly the model will be training here as well. So it actually zips along pretty quick. And so we're getting validation accuracies around 0.97, which is pretty good. And sure enough, our test accuracy is around the same value, 0.97. So that's very good test accuracy after only 14 epochs. And to prove that out, we can just plot these results, and sure enough, it still sees a 6. The rest of these are correct. If you're trying this along with me, then yours might have come out so that they're all correct. This is just a random smattering. I think the first 10, or random 10 out of the set. So yours may have come out all correct, and you may notice that your model either stopped training or continued training at a different point, all due to the way that the randomizers are set up. So that kind of does it for this first deep learning bit, and I hope that made sense. I know it's quick, but this kind of sets us up for a break as well, Danny, if we want to think about how we're going to go about the chat. I mean, one thing is here, do we have any questions that are obviously need answering from this section? If you want to put your hand up. And we have Megan Foss, I guess. You want to ask something, Megan? Nope.
Sorry about that. I think it was left up from earlier. I'm just playing around with the code right now.
Okay, cool.
Alistair?
Yeah.
Alistair, you have a question?
Yeah, so a few things. One is I wanted to check, what did you do at the top in order to make it run faster?
Okay. Well, the thing to do is to change this runtime type. So under runtime, in the back end of the cloud, as you can imagine, there's all sorts of different machines living at Google's end, and some of them have no hardware acceleration whatsoever. They have a regular CPU. So that's what they plug you into by default. And that's fine. It's still okay performance, but if you really want to crank it up a notch when you're doing deep learning and you're using a lot of these specialized layers, you're going to want to change this accelerator to GPU or buy one for your local machine and try using it there. But this is easy because it changes in the cloud immediately. And when you get this check mark, now you're going to be able to do these training runs a lot more quickly. So this, if we ran this again, you're going to find, well, first of all, I didn't reset from where I was, so, but that's obviously a lot faster than the way it was training without acceleration. I'd always kind of suggest turning it on if you're doing this kind of application. It will make your life a lot easier, and if you're doing anything with real images, or if you're doing anything, you know, any kind of serious sort of research, you could be sitting there for, you know, minutes and minutes or even tens or hours before you notice, you know, that the thing, it's not that it's just waiting, it's that it's actually processing in the background and it's just never going to get there. So I would turn it on when you're doing any of this deep learning stuff. Do you have any other questions? I think we can go to the break here too and decide about what we want to do with the chat, I suppose.
Yeah, so what I'm doing, guys, is I'm making you all presenters. This could be dangerous for us, but it's probably the only way, I think. Well, actually, I just made several people a presenter. So Alistair, for example, I'll be interested in, you know, if you can see the chat now. And a few others, Brendan, Brent, Chow, David, you're all presenters now. Can you see the chat?
I'm not able to find it. Where is it? If it was
on the tray, the little tray that's in the. If I bring this up here, well, maybe Andy can show you. Andy, just show him the tray where the chat button is.
Okay. So you can see right next to this raise your hand business, there's a conversation thing. So when you click that, it pops up this meeting chat, and if anyone can type in there, then that's a good sign.
My UI is a little bit different, but I have seen that before, and it's similar to, I have that, but similarly at the top of the screen, and I'm not seeing it.
Okay.
Oh, well, that's really odd. So I think what we're being subject to here is, I noticed this with interaction with Dalhousie back a while ago, because we both own licenses, and I suspect Saint FX is the same situation. That means that because you're logged in with your Saint FX email address, Microsoft doesn't want us playing together, I guess. Now, I'm not sure if that's exactly, because I think Sid, am I correct, Sid, you tried logging in with just a Gmail account? And
yes, sir. Like I tried to use Gmail account, but it says like it has to be Acadia tenant.
Yeah, but you can be made a guest. So a guest can be invited. So that's the other thing I can do, is try inviting each one of these people, I guess. I'll look into doing that right now, okay? Anyway, I guess I will turn those other people back to attendees. And since that did not work. Anyway, everyone take a 7th inning stretch here, and we'll come back to you in a minute.
There was something else about the code I want to bring up, if that's all right.
Oh yeah, for sure.
Yeah, sure.
So one thing I noticed is that even though all my code ran fine, like it gave the output at the end, etc., when it did like the part that actually would take a while, strangely enough, even though there were no actual errors, the output itself tacked on at the end of each line right after the accuracy, no space or anything. It just tacks on a warning saying TensorFlow, early stopping condition, a metric,
So
is not available.
yeah, that's where you want to change this monitor business. I think I kind of went through this quickly, but on line 2 under step 3, that's where this early stopping is defined. So the monitor, instead of reading val ac, it should be val accuracy. So if you change it to that, then that warning message won't pop up, because then it's monitoring the right thing, basically, in a log file.
Yeah,
So,
yeah, that looks good. Thank you.
no problem. Okay. So I'm going to turn it back over to you there, Danny, for the next section, but I'm going to go and get a quick glass of water here or something too.
I think I'll do the same. So it doesn't want to allow me to invite people who are not on the Acadia list for some reason. I don't quite understand what's going on here. I just tried, let me see. Who's Alistair? Alice says you can't, okay. Copy join info. Copy to clipboard. Yeah, just not having any luck with this chat thing. I've not seen this happen before in this way.
No.
So turn it off. It's really weird.
Yeah, it's interesting that Sid's approach there did work for some people at Acadia.
Yeah,
but
that's when I try to invite people, if their address is not an Acadia address, it just keeps coming up saying we don't know who this is.
Right. There could be some kind of license incompatibility or something.
I mean, I have had people join in and use the chat who we have had, like I've had them part of the ad group remotely, and they've been able to join in, except for Dalhousie. When there was a Dal address, that person then had to log out and log back in as a Gmail account, else they wouldn't see the chat.
Oh, weird.
Yeah.
Something going on there, but that's a good question for us to.
So there's something I want to flag quickly about the email that was just sent out.
Yeah, the email about the you're completing the workshop kind of feedback form.
No, I mean about a new link too, so that we can use it.
Yeah, I just send you the email. See if that works. I was just testing, like if that link, like you open that link in MS Team and you could able to type in the message in chat. I just send you the link.
So I want to flag it now because what I found is that that link, and when I tried to click it, nothing opened up. So I want to flag it now so that we know, so that people aren't just like stuck or something. But I was able to use the old link to get back in.
Okay, thanks for letting me know.
So Neros, that was the link from up. Let me see. I'm going to share my screen here.
That was the link I sent to a couple of Acadia students, and it worked. Like they could able to chat, but I just sent to one.
That was the link from up here.
Yeah.
Yeah. Yeah. And I was thinking of that too, but this is where if I try to put in, if I try to put in, like, for example, Alistair's email address here, if I attempt to put that in here, it just keeps coming up, and so we can't find any match. And if I hit enter, it doesn't want to do anything. So that's really annoying. Anyway. Oh, okay. I think the best idea is just for anybody that has any questions, please speak up. We can at least hear you. And why don't we just take a poll right now? Are there any questions that you have at this point?
Are we going to cover methods of how many hidden node layers that we're going to choose, cover like the optimal kind of number of layers and nodes to choose for the network?
Well, I can talk to you about that just briefly. I think maybe I'll put my headphones in here. 1 second. I'll be a little clearer. Okay, everybody hear me all right? Okay.
Yeah, sounds good.
So there's a bit of science and art to this answer, and what I'll do is I'll just make a blank and draw something here for you. Grab a pencil. So the science part is that, as you saw, if we have just two inputs, we saw that if you don't have enough stuff, if you don't have enough representation in your network, it's not capable of making models. So let's assume that we've got a classification problem that's kind of like this. So we've got, this is class A and this is class B, and we want to separate those two. We know that this simple little neuron with no hidden nodes, the best it can do is something like this, so it doesn't do a very good job. We can increase the size of this network by putting in a hidden layer like that. So that begins to tell you something, that if you've got something that's more complex than a very trivial classification, you're going to at least have to have one hidden layer of nodes. And with two hidden nodes, what you can do is you can have, one that kind of, well, more importantly, if we create one with three, let's put a third hidden node here like that. If we have three, then we can actually create one discriminant function is sometimes referred to as a hyperplane this way, and another one this way. So now we can kind of carve off all of B, and that can be kind of useful. Now, another thing that you can do is to take and add yet another layer. So now we still have our two inputs, but now those two inputs are coming into a first hidden layer, H1, and a second hidden layer, H2. And what you have now is the ability to create two kind of little triangle areas like this, but one that's over top of another. And then this piece here can kind of be etched out of it. So now you can have much more complex and convoluted sort of discriminant boundaries, ones that have little concavities in them, and you can cut out little bits and shapes. So what this says is that two hidden layers really gives you the ability to kind of carve out arbitrary concave, these are referred to these are called convex hulls, a region that can be used to kind of demarcate a portion of the input space. These are little concavities, mean that no longer are they purely convex hulls, they have concavities to them, so they can do even more complex things. And that's only possible if you have a couple of layers. So if you have any complexity to the model, you're probably going to want a couple of layers minimally. Now the next question is, well, how many nodes should I have on a layer? Well, given that this surface is really round, if we want something that's really approaching something that's smooth like this, then these triangular shapes not going to kind of do it. We're going to have to add more nodes in, many more here, in order to kind of create a series of little, that kind of carve this up really nice into kind of its chunks and pieces like that. So the science bit here is that we know we have to have a couple layers at least to create something that can deal with something really complicated, or relatively complicated. The number of nodes on each layer, though, is more of the art, and that comes down to like setting up some kind of a, typically it's called a grid search, where you might start off, let's say, with initially, just 2 hidden nodes, and then try 2, and then 4, and then 8, and 16, and then 32, and take a really principled approach where you're trying number of hidden nodes in one layer, and then get to a point where it's doing pretty, it's not getting any better, and then you take the other layer, you start adding them in that way. So you kind of take that methodological approach, but that's still a bit of an art. It's kind of a methods type of approach. So the combination of those two things is how this tends to be dealt with. Now, the more modern technique, because of all the horsepower we have, is that for a problem like this, you just take a whopping big network with all kinds of nodes in the first layer and all kinds of nodes in the second layer. And if you're really uncertain, you even add another layer, particularly if it's imagery and things like this. Clearly, the problem here for a processor that doesn't have a lot of speed is it's going to take a lot of computational time, and you got memory here too. But if you have lots of that to play with, this is not an issue. And then what you do is you just let it train while using something like the early stopping to prevent the model from overfitting. And essentially what's going on is that if you take a connection like this, it starts originally as being a value close to 0, a small weight value. If that weight value remains close to 0, then effectively, that connection isn't really there. So there are methods that can be used to reduce the effective number of weights in the network down to a small number, even though you start with a really large number. So increasingly, as our computing power and memory gets bigger and more capable of, having big networks are not a problem, and having big nets are usually what you always want to solve any problem, because a big network can solve this little problem just as well as it can a big problem. The only issue is how much costs are going to be in terms of length of training and things like that. So I don't know if that completely helps, but it gives you a bit of a flavor as to where we're at. Early, in a lot of early stuff in neural network training, they'll kind of emphasize, well, you got to get your architecture right and all that sort of thing. Well, the truth of the matter is, if you've got 2 layers with enough nodes in it, it's going to work. It's just a matter of how long it's going to take you to train. If you wanted to train faster, you could reduce the number of neurons in each layer down a bit more, and it would build, a model faster. And if you knew the ideal number, like we did for like the XOR problem and things like that, then it can build great models and very quickly. But the getting it quickly is not so as important. Building accurate models, that's really what you want to do. Okay, I'm going to delete that and go back to this, and let's carry on. I'm going to talk to you about convolutional neural networks. The next step in that, moving to more deep and complex networks. The idea here is that we essentially take advantage of our knowledge of the input space. And this was in the insight going back to one of the early names I read about was James Albus, and now Jan LeCun, who saw that we can take advantage of our knowledge of both the input space and knowledge of how our visual system seems to work. So if you think about a pixel in an image, such as this one right here, so this one pixel in the middle of the little red area, that pixel has other pixels around it, and those pixels around it are likely about the same. We can make an assumption that they're going to be similar color, brightness, sort of thing. I mean, look at a pixel like in the dark area on the person's hair. All the pixels around it are dark, and even this one, most of them are dark. There's one light one and a couple gray ones, but the assumption still holds. So the idea is that we're making an assumption that the pixels adjacent to any one pixel are going to be similar in a way. So we're going to take advantage of this. So we can use this background knowledge as something that we can then build into our network to help us reduce the number of weights in the network, but at the same time allowing them to train even better with the same number of training examples. So your eye and your fingers and your nose and all the things that you sense the world with actually take advantage of what's known as a receptive field. And a receptive field for a neuron is actually the region of the input space that it senses around it. So, so how do we properly design a receptive field? And we're gonna focus in on images. So consider a task with image inputs, and the receptive field needs to provide some information that can break down the image into chunks that are going to allow us to be able to better recognize what's in that image, be able to at least classify this as being an image of a dog or a cat, or in this case, Einstein. So let's just talk about what kind of receptive fields could we make here. Well, here's one really naive one. We've got the inputs from each pixel of this image coming into the first layer of neurons. And we might have, you know, if this image is say 1,000 by 1,000 pixels, this might have 1,000 nodes here. And where every single pixel comes forward to each one of these nodes. So that would be, so if it's, a 100 by 100 image, this, and we had 1,000 units here, that would be 10 to the 7 edges, 10 to the 7 connections here. So that's a really big network, and we haven't even started to try to classify this yet. You know, we have to move on to another layer. So the problem with this is that anything local in the image, like identifying a person, a human eye or a nose or a mouth, is it's kind of lost. I mean, there's no, as it's saying here, local spatial correlations. Things that locally that might identify an eye versus a nose are kind of lost because everything is dragged into the first neuron and every other subsequent neuron. Although each of these can be trained individually, that, you know, and it would be helpful, it's just not the best way, effective way of doing things here. Now we can think of what we're going to call locally versus a globally connected network. We're going to have receptive fields that, you know, there's one here and then another one here and another one here and another one here, and each one comes back to its own little neuron. So we've covered all of the input space, but these are fixed on the image. And now for a 100 by 100 image with 1,000 of these, we have a filter size of 10, so that's 10 by 10. We've got 10 to the 5 weights coming back to all of this. Not as many, a little better. Turns out it's going to do fairly well as long as the face is registered, it's called. What that means is that if we did some pre-processing the image and place the face, so knowing that it's faces, and we want to identify, you know, is it Einstein or if it's someone else, then as long as we place the face such the eyes and the nose and the mouth were roughly in the same place every time, then a network like this wouldn't do too badly. But if the image of the face is somewhere up in the corner or down in the bottom left or something like this, then it's not going to do very well. The face would have to be registered so that the location of features of the face are in the same place. What we want is something that can pick off, for example, the character 8 that you're seeing here, any of these character 8s, regardless of where they are in our input space. So objects can be a dog or a cat, or this figure 8 can be moved along translationally or up and down. It can be rotated, and we can zoom in and zoom out. And in every case, it's an 8, and we want systems that can identify 8s in that way. So what can we do? So these are the 3 kind of dimensions of variance that you can have: translation, rotation, or scale. We want to be able to handle all of those. So the solution turns out to be something called convolution. And the idea of a convolution is actually mixing of 2 functions. to create a new function that's more useful than either one of the individual functions. And it turns out by doing this that we can actually reduce the number of weights in the network through a sharing of weights at each one of the layers, or filters it's called. And if we do this several times up through the layers, then we gradually create more abstract feature filters, things that can identify stuff in the image, all the way up through a chain. So let's just dig down on this a little bit more. So first of all, what the heck is a convolution? Let's take a look at this guy's image once more. And we're going to focus in once more on this pixel right here and its surrounding pixels. A convolution in 2 dimensions, because this is an image of 2 dimensions, it takes 2 functions and it produces another function. So in this case, we can think about this mixing of functions as taking a matrix and sliding it over top of another matrix, because the image is a matrix. So the first matrix is our convolutional kernel. It's this little 3 by 3 centered on this pixel. Now, if we think about just this one location in this image, and if we think about one particular type of kernel, it's a sharpening kernel. So its job is to take the image and to kind of sharpen up the edges, if you like. So this kernel passed over this entire image, producing the sharper contrasted image. And it has these values of 0, -1, 0, -1, 5, -1, etc. So this has been handcrafted, and this is what image processing people did for years and years, is they created these interesting filters that they would pass over the image to create features. They would do it manually. So if we have a feature like this, which is somehow created, what we're going to do is end up creating these by training it. We're actually going to learn what these filters are. But if we've manually created this one, the way it would work is as follows. We would take the value of this gray pixel right here, which is 173. So if you look at this 3 by 3, bring it over here. Here's the values, grayscale pixels. That's 173. This is 255 because it's bright white. 254, step down. This one's 54, 140, 46, etc. We take the pixel value and we multiply it by its corresponding value in its kernel. So that's 173 times 0 plus 255 times -1, 254 times 0. We do that all the way down and we add those all together. Now that should look familiar to you. This is the same idea as the weights times their inputs. So the 173 is the input, and the times 0, the 0 is the weight. The -1 is the weight. The 5 is the weight. So this is just the inputs times their weights. And then we add them all up and we get 97, and that's what goes in this pixel. So this is a kernel that's been manually created, and when passed over this image, is able to transpose the image. We can also use it for identifying things. We can identify, for example, an edge that's going in this direction, or an edge that's going in this direction, or a really bright area, or perhaps a little square cubic area or triangular space. We can create different kernels like this. Even better, it's possible that we can train a neural network to learn these from lots of examples of images. So just look at another example. This one's a blurring filter right here. This one's a edge detector like this. This is called an embossing kernel. This is one of those ones that kind of softens the image in certain ways and creates like a little feature in it. So let's take an image. The original image looks like this, really simple numbers just to make things easy. And we pass our kernel, this embossing kernel, which is a 4, 0, -4. And the diagonal, all the others are zeros. And so this becomes 0 times 4 plus 0 times 0 plus 0 times 0 plus 0 times 0, all the way down to finally 2 times -8. And if you take and add those all up, you end up with -8. And that's what goes in the corresponding point of where this kernel is centered. One of the things you'll notice here is that we can't seem to get to this outer corner, this outer edge. So oftentimes what's done within these systems is we add another layer or two on the outer edge of just pure white pixels. And that allows us then to get out to this corner and all along this edge and also along that edge, a little trick that's tend to be used to generate the kernel. So that's what kernels are capable of, and convolutions, as we pass over images, we can use them to detect features in the image. What we want to be able to do is to train these kernels in a network. So if we have a kernel set up, what we can do is pass it across the image like this, and what we do is record the value that it generates at each point in a new layer forward in our network, like this. So we end up with a whole bunch of different values as that kernel has passed over. So you'll notice basically what it's doing, it's scanning the image. And you can think of it as scanning the image for some feature, you know, like a place where it's light and dark, or where there's a line that goes in this direction. It's looking for that. And the value that it gives you here indicates whether it has found something like this or not. The higher the number, the more the more it's found that particular region. So convolutions can be really useful if we have them. If we've got them in place, they're really useful. And we can have multiple filters to indicate different things. You know, like this first filter, it looks for lines in this direction, and this one looks for lines in that direction. This looks for circles. This one's look for triangles. It's that type of thing that we had those filters, and they can produce. You know, the multiple kernels actually can build multiple filters, and your images nowadays, of course, are not just grayscale. They're actually three different layers: blue, green, and red. And so that means we even need more of these filters in order to produce what we need the next layer up. So the convolutions are great for identifying features anywhere in the image. That deals with the translational aspect. The rotational aspect can come from just the learning algorithm itself. It can just learn to tilt it a little bit. We don't have to deal so much with that one. That can be just from a variety of images of the dog that's sitting at different angles and things like this. What about the issue of the camera being 10 feet from the dog versus 5 feet from the dog versus 20 feet from the dog? The dog's going to be different sizes then, but it's the same dog. So pooling layer is used in this case. And the idea of a pooling layer is that it can take and transform an object in the image of one size to a standard size, or from different sizes to a fixed size that we can then use. And there's some really interesting and simple methods of pooling. One of the simplest is called max pooling, and it scans, again, it's another type of convolution. It scans across the image, and it just looks for the highest value in the image, and makes the pixel in the next layer that value. So you can kind of think about this as being essentially that it looks at a 2x2 region here in the image, and it said, well, what's the brightest spot? And I'm just going to, in the next layer, which is a reduction of that image. So now this 2x2 area, the original image, becomes just a 1x1, and I'm just going to say it's 45. The other way to go is that you compute the average. You take all these numbers, add them up, divide by 4, and you put the average value in here. The reason why the first one's one of the most popular is it's really dead easy to calculate. This one takes more math, and this one even more mathematics. But they can be useful for certain problems. But this max pooling is one of the cleverest. So again, the idea here is that it's essentially taking a large image in which might have like a cat's ear or a cat's eye, and it's reducing it down to the same size, and that helps us to better identify that it's a cat's eye or corner of the car or whatever it is that we're looking at. So we've got this two-stage kind of two parts to a stage of convolution. We've got the convolution proper, which deals with translation, anywhere is up, down in the image, and then pooling deals with the scale aspect. This changes in scale. The rotational part is purely from training the neural network on various images of the characters, in our case, the digits at different angles. So the whole system then is composed of layers of stages: convolution pooling, convolution pooling, convolution pooling. That's what we're seeing here. This is a convolution followed by a pooling layer. And then this feeds another convolution followed by another pooling layer. And you could have a third one of these. And then what you do is you take all of these filters and you just kind of feed them into a standard hidden layer. It's called the dense layer of neurons. And then you step those down to, in this case, we're interested, I guess, in identifying the characters A through G or whatever. And so that would be 10 outputs to allow us to indicate, you know, this would come on, the first output would come on if it was an A, the second one would come on if it was a B. Right? So you can think of what's going on here then. So if we're trying to identify types of cars, classes of cars or trucks, then the first stage builds edge detectors. The second stage builds small abstract feature detectors based on those edge detectors. And the next one builds even more complicated, we could say, subcomponents of a car, tires and mirrors and, you know, this chrome sort of front piece on the car. And then finally, the output layers take these features together and say, oh, that's, you know, an antique vehicle. This is a new Chevy truck. That's a Honda Civic, that type of thing. So this has made incredible leaps forward in terms of image recognition, audio recognition, being able to recognize voice, this type of thing, even as you're speaking in real time. And you can see that starting in 2010, on the ImageNet data set, which is a really large data set with thousands of different classes of objects and millions of images. It's really interesting to go and look at that data set if you like. It's grown over time. It originally had only like 1,000 classes, and I think maybe 20,000 images or something like that, but it's grown more and more. In 2010, we were getting a 28% error on what's known as the top 5 error. And now we're down by 2015 to only 3.57% error on that top 5. And it's gotten even better since 2015. And this is, the other thing I'll point out here, look at the layers. These are really shallow, like 1 or 2, maybe 3 layer networks, 8, 19 layers, 22 layers. This one has 152 layers in it and makes use of that ReLU type of activation function that Andy told you about. So we're going to now try learning the MNIST data set, but with a CNN type model. And again, it uses a validation set to tune the model. So let's jump over to, just before I leave this, at the end of each one of these sets of slides, there are some additional reference bits here for the keeners who want to kind of look ahead, something else. So, oops, sorry, let's go back here and go to MNIST. And make sure I make this a little bit bigger. Hopefully that's better. And right, we've got again same structure as things. Nothing really new here, or here. Loading in the data, doing the same with it, preparing it in the same way. In terms of configuration of the network, certainly is going to be something different. We're going to make use of the built-in TensorFlow libraries for convolutional layers. And as you can read in a little more detail here, what this does is sets up the first layer to receive the 28 by 28 pixel images, which only have one layer of color, which is the grayscale. Now, if it was a regular full color image, this would be 28 by 28 by 3, the red, blue, and the green. images. So that would be that's a 3D tensor feeding into the network. The activation function for all the nodes in this layer is the ReLU function, and we're going to have 32 kernels, essentially filters, that are going to be constructed from this. And each one of these kernels are 3 by 3. So we've got these little 3 by 3s that pass over that 28 by 28 pixel, and they're all going to be initially random, set to random initial weights. What the model's going to do is learn to set those kernel values so that they work together to produce the appropriate output value that we want. They're actually going to be trained. And this is what is thought to be happening within the neurons of your occipital cortex of your brain, feeding, just as the optic nerve from your eye feeds into your brain, this whole sort of thing supposed to start in this sort of way. Now, that's a very gross kind of level understanding, but it seems to work pretty well, and it is based on what we see in the actual mush of your brain, at a crude level anyway. The next thing we do is the max pooling. So we take a 2 by 2 filter, all right, and we apply it to what we get out of this, the 32 filters. Now remember, every one of those 32 filters look like this. So each one of, this is a kernel, it generates a filter, which is an array of values that's produced by passing the kernel over the entire image. So it creates a whole bunch of numbers here. That's known as the filter. So we take that filter and then we apply a little 2 by 2 pooling layer to it to generate a condensed form, a shrunken form of that image, where we're trying to scale everything down to a standard size so that we can better identify that feature. So that's what this max pooling layer does. And then we do this thing that Andy mentioned to you called dropout, which the idea here is that we take 25% of the nodes at random and we drop them out each iteration. And that is a method of regularizing the model so that it can generalize to images that it's never seen in the future. So we've done this once, and then guess what? We do this whole sort of thing again. And this time we just got to put the lines right together. We put some comments in here, but the second one we just, and now this one, notice, is the kernel size is now just 2 by 2. Still it's an activation ReLU. Notice that we don't have to put in the input shape. That's the beauty of Keras, is that it does a smart assumption. It says, well, I'm going to assume that my input is whatever you ended up with on the last layer from the pooling, right? And then we do another pooling layer. So this is the equivalent of the second one right here. So this is our second convolution, and then our second pooling. That's what's happening right here. And once again, we do dropout on this layer as well, kind of throwing away, just for an iteration, some of the nodes. Next iteration, those ones can be back with a probability of 25%. And then we take that last output and we kind of condense this all down to a flattened layer. So we flatten all those neurons at the output, and then we just pass it through another layer of 120 neurons, just like a standard hidden layer, right? And we still apply dropout to that. And lastly, we pass it through the final output of 10 neurons. So its size of that layer is number of classes, which of course is 10. And in this case, the activation function is softmax, because we want just one of those 10 neurons to be maximally active as compared to all the others. Now this little statement right here, Keras says, give me a summary of my network. And that's what this is telling you. It's telling you basically the architecture of the network. So that lays out the graph architecture of the network. We then compile it in the next step. And this compilation, again, does early stopping and records all the accuracy and all the good stuff. And again, turns its verbosity on so we can see at each iteration how well it's doing. And we're going to train this just for, what are we training it 4 here. I'll check because it's stopping. We're training it for just 12 epochs, yeah. And once we've done the training, then we evaluate the model once again on the same set of examples in the first 10 in the test set. So if we run this whole thing, and I haven't turned the graphics processing on or anything, so it's going to be initially fairly lengthy. So the computation takes a little bit more here because it's passing over that kernel over everything. But at the same time, there's not as many weights in this network as if you it kind of just a standard sort of structure. So there we go. It's trained. It's predicting 93.37, which is not as good as the last network, but I'm sure that if I went back here and, you know, training set to say 1,000, sorry, 1,000, let's make it 30, something like that. Yeah. And the other thing I can do is go up my runtime and let me just check. Oh, I do have the GPU on. Run all. I thought it kind of moved along rather quickly there. See if it does a little better. And it's getting a little better, 95. And if you train it even longer, it'll get even better. It's up around 96. So again, the advantage of this is this idea, as you see in this diagram, of passing over the original image, a kernel that's essentially scanning for features. What features it's scanning for? Oddly enough, it's scanning for features that it's learning. It's creating the kernel on the fly to allow the whole network to work together to identify what digit 0 through 9 it is, and coming into the image, into the network. Okay, so hopefully you've all had success in running that code. Any questions about that, or did you try something interesting you might like to share with the rest of us? Okay, if not, I will pass things back to Andy. I'll turn off my sharing here, screen sharing.
Okay, thanks, Danny. Let's give this a try here. Kind of running late, but I think we can, if we give me 20 minutes, I'll have this banged out. Let's see here. So up until now, really what we've been looking at are sort of episodic learners and models that accept an image in some point in time. It doesn't really matter what it's seen previously or what it's about to see. If I feed the classifier the digit 4, it'll tell me it's a 4. I show it a 2, and now it says, okay, that was a 2. But imagine if I was telling it, okay, instead of just seeing that digit 4 or the digit 2, instead I'm going to give you a series of images. And this is the series. It's going to go 2, 4, 6, and now tell me what's coming next in that series. Now, by using the temporal information about, you know, that these are even numbers, it might be able to infer something about what's coming next. So beyond just looking at the pixels, it can say, well, I've seen in the past that they normally are just skipping along by 2 here, so the next one's probably going to be 8. Well, when you have information like this is called a time series, and there's inherent temporal information in the pattern. So something about what you've seen in the past should probably inform what you're about to predict or what you're seeing currently and what you're detecting. So when you have data like that, the thing to think about is this type of neural network called a recurrent net. So recurrent neural networks are a special kind of neural net that is still a multi-layer network in a sense, but only in the sense that it's through time rather than having multiple layers itself. So a multi-layer feed-forward net is a directed acyclic graph, whereas a recurrent neural network is a digraph, and it has cycles. And what happens is these cycles can act as a memory. And you'll notice the subscripts here, exit T. So this tells us something about, in a regular multi-layer network, we have input nodes that are sort of aligned this way. In recurrent nets, we're probably going to be drawing them out so that the inputs are coming in through the bottom here. And they will have a subscript that tells you something about their position in time. So these inputs at this current time are coming in and being fed into this same network unit at the next period in time. So at exit T+1 now comes in and is being fed to the same unit. So you have these cycles that imply memory. So the hidden state of the recurrent net, that's what can carry along this information about, potentially many number of previous steps. So it's this idea of sequence that should trigger you to think, oh my gosh, I need something that can represent time, or that can in some way incorporate patterns through a temporal period into our network. And you can do this quite naturally with recurrent neural nets. And we'll talk about a couple of different types of neural nets, and one specific type that we'll do a simple example. And you'll get to see how they very naturally can model data that has a temporal aspect. So as I was just sort of talking about in the previous slide, this idea of recurrent nets with a cycle like this, when we expand this out, so we call this rolling out this network, so that we're looking at it over a period of time, doesn't imply that there's multiple, it doesn't imply that these are multiple layers per se. These are just different time steps with the same units. So that's denoted here with the subscripts 0 through T. And at each period here, you're going to have some activation that's passed to the same unit at the next step in time, and it's going to produce a different hidden output at each step in time that could potentially be passed into other units. But we'll keep it quite simple and just imagine that we only have one unit in this current form of recurrent neural net. So one thing that this implies is that, as we mentioned, you do pass something on to yourself after each item is shown, after each data instance is shown. So at time 0, 1, 2, you're getting information about the previous step. So that gives you some implication that there is a short-term ability to remember what was just previously seen. So the previous internal state is available to the unit at the current state. So it can be used to help make a decision about what you're seeing or what you're liable to be asking to predict. So hidden layers now have the task of mapping both the external input, but also the previous internal state, right, to some desired output. So that's the idea of a short-term memory. And it can do this pretty well for very short sequences, but as you can imagine, it doesn't necessarily translate into longer-term sequences. A recurrent neural net is great for learning, for example, a song, or it might be good for doing something like when you're texting and you want to know what word ought to be coming next, or you would like it to be able to suggest something that's coming next. So in a song, and I mean, texting is just another type of song, really. If you think about it, you're just creating a composition of words. In a song, you're creating a composition of chords or notes, and one's coming after another in some way that sort of makes a compositional sense. So you might say A, B, C, D, and then, produce some sort of character that says, okay, I want an output now based on what you've seen in the previous input sequence. And well, lo and behold, it might spit out an X. And when you ask your phone to do this kind of thing, it gets pretty humorous because you can spit out all sorts of things based on what it thinks you've set in your input sequence. So an X then gets fed in, and you ask it to produce another target value, and maybe it says Y goes to Z, and Z goes off to something Q. It isn't, it doesn't really know what sort of pattern that you're trying to generate there to some extent. Okay, we've talked about vanishing gradients, so I'm going to skip over this. The idea is still present in recurrent networks, and as you add more hidden layers, the training becomes much slower, as we talked about. So that problem isn't really going away. And moreover, recurrent neural nets have difficulty, as we suggested. I mean, you might imagine they have difficulty with longer range time dependencies because it's just getting the state from the previous activation. So how would it, have any sense of what it's seen 15 time steps previously or something? And, today we're looking at compositions that, sometimes a sentence can be tens or hundreds of words or something. And we're looking for auto-completion to make any sense of it. I mean, it's asking quite a bit, but we'll talk about how these methods sort of helped overcome this issue of longer term dependencies and vanishing gradients. Specifically, we'll talk about the second one, the fancier modules that were designed in the late 90s to handle long-term memory dependencies, and they're called long short-term memory units, or we just call them LSTMs. Okay, so I mentioned LSTMs came about in around 97. That was Horschreiter and Schmidhuber that solved the problem of getting recurrent nets to remember things from a long time ago. And we say hundreds of steps here, but initially, it's amazing that if you think about it, it's amazing that it can really remember patterns and sequences, as we'll see in the demo, that are even relatively short, because you'll be able to identify the amount of complexity even in short patterns with temporal information. The human eye isn't even terribly great at spotting them, so it really is an interesting concept, and LSTMs are an area with lots of promise in this respect. So we'll see here, this is sort of like the rolled out model of the architecture that I showed in the previous slides, where the inputs are coming in at each time step through the bottoms, and outputs are being passed along through the sides. Outputs are also passed, the hidden activations are also being passed potentially to other units that may exist here, but we'll again just consider single units for our purpose. So Horschreiter and Schmidhuber designed a memory cell, essentially, that use logistic and linear units with multiplicative interactions. And the key is that these basically can retain information from the distant past that may be important to being trained. The importance is being trained into the model as it goes along as well. So key to the whole process is what's called gates, and there's a series of little logic gates that are all responsible for these memory processes. Information gets written to the cell when the write gate is on, stays in the cell when the keep gate is on, and can be read from the cell when the read gate's on. So just looking at this a little bit closer, it's these three gates, essentially, here and here, that control what's happening on the memory or the cell state. And you can think of the memory or the cell state of the unit being this backplane, this vector transfer on the backplane. So notice that cell and hidden state are accepted from the previous state. So this would have been the cell state, and this would have been the hidden state from time t-1. Those are accepted at time t. And the new cell state and new hidden state are passed into the unit at the next time step at t+1. So the three gates, again, that control the memory functionality are keep or forget. Sometimes this is called the forget gate. The next one is usually referred to as the write gate. And the third is the read gate that allows the data to come off the memory and be combined and passed into the next activation point. So to make this a little clearer, I think the thing to do is to just get out our Jupyter notebook and let's take a look at the Keras RNN notebook. And for loads more on time series, we've got a couple other links here. And I would also, I normally start with this little demo, but I will leave it sort of to you to see the aficionado demo. This is a neural net that's been trained. It's a recurrent net that's been trained to detect different types of music and classify it. And it's running against a hand-designed model that looks at the sequences of notes that are being played and tries to get a classification of it over on the right. So these are little experiments that were done, to indicate the difference between what these long short-term memory modules are able to do versus what the way that a human might interpret these different kinds of music. But you get the idea. They very quickly do classification, and it's quite a strong indication that it's able to tell what type of music is being played. So these are all trained with labeled data, and it can get on to a certain type and sticks with it rather than bouncing around like a human model might. Anyway, let's get on to the notebook to keep this moving along. So you want the one with the RNN appended on the end here, and it's set up the exact same way as the previous notebooks. There is a little bit of background on LSTM networks. We kind of blew through it on the slides there, but for the sake of time, I've kind of filled in some more of the details, and you can really get the gory details if you want to look up the magic of LSTM networks. So there's a few links here that you can use previous to step 0, a little bit of background. But again, I'm just going to delete the previous outputs so that I have a fresh slate here. And we're going to start with the environment setup. So this stuff's going to start looking familiar to you, and it should feel like you can see that things are going right. The messages should start to look familiar. So step 1, there's going to be a little bit of difference here. We're no longer working with MNIST. Like I said, this is recurrent nets, specifically LSTMs, are great for learning songs. And a song can be any kind of temporal pattern if you think about it. This could be, this could be data in a sort of a stock environment, or you could have any manner of temporal or sequential time series data, I guess is what I'm looking for. So the time series in this case is what we'll call a song, okay? And songs are just made up of letters from the alphabet. And in this case, song patterns go from left to right, and they're rows, and their elements are columns. So this song is XXAH, FECED, and the song title we'll call M. So the last element, this last column, is always going to be the target. So those are our labels, if you'd sort of like. These have been made not just arbitrarily, but like I said, these do contain important temporal dependencies. For example, you'll notice here I'm saying that the songs with labels M and Q only differ in 2 elements. Okay, but those elements occur at the very beginning of their sequence. So songs labeled M and Q, if you look at these, they're really similar. M goes backwards, it goes B, similar to Q, B, E, C, E, F, H, so still pretty much the same, A. So it's only back here at B differs from X and C, so it's at the very beginning of this sequence. And remember, this model is going to see these patterns in sequence and have to make this prediction about what song it's just seen based on the ordering. Really, this is the temporal nature. So so there's also this difference between N and Q and M. So if you look at N, it's actually offset by 1 here. So it also has an E, but it's offset by 1 from the song M, and this E is offset from this E, etc. So we have this behavior. It only changes like back here. So it's able to make these kind of distinguishing characteristics, or identify these characteristics automatically. You know, like a human eye, if you're looking at this, you right away wouldn't probably be able to pick out the similarities and differences between these various songs. And if someone was to play them for you a couple times, you'd probably be just scratching your head saying, I don't know what you think I'm supposed to be able to, you know, make heads or tails of which one's which.